All right, this is going to be review video number 8, how to write an orbital diagram. Orbital diagrams are going to be little arrow diagrams that describe the direction that electrons are spinning within a single orbital space. So recall that within different shells, there's going to be multiple types of orbital spaces, S, P, D, and F. And even within those types of orbital spaces, there could be more than one of those orbital spaces within the same shell. So one important thing to note is that any electrons that occupy the same orbital space have to be spinning in opposite directions. And the reason for that has to do with the charge of electrons themselves. We know that electrons are negative, which means that typically they should repel each other. They should want to be as far away from one another as possible. And so to make it possible for two electrons to occupy the same orbital space, they have to spin in opposite directions because that opposite spin allows them to associate more closely. And the way that we represent those opposite spins is with this little up half arrow and this little down half arrow. So you'll see that a lot in orbital diagrams, and that's why I say that it's kind of an arrow diagram, because we're using arrows to represent electrons. These horizontal lines underneath the arrows represent orbital spaces. One line represents one orbital space, and each orbital space can hold 2 electrons specifically. All right? Second thing to be aware of is that electrons will fill all available orbital spaces before they start pairing up and occupying that same space. And the reason for that is basically what I just said. We know that electrons are negative, they tend to repel each other. And so they're going to be as far away from each other as they can possibly be until they have to start occupying that same space with those opposing spins. So let's say you were writing out an orbital diagram for a p set of orbital spaces. So let's say it was 2p3. That means that you would distribute those 3 electrons on 3 separate lines, rather than doing something like this. This would be incorrect, because while you would have distributed the 3 electrons, you paired them up when they didn't have to. All right, so realize that electrons are going to spread out as much as they can within subsets of orbital spaces before they'll start pairing up. So this would be the correct way to represent them, whereas over here would be incorrect. When you're drawing out an orbital diagram, depending on the piece of the electron configuration that you're doing, you're going to draw a different amount of lines, because every type of orbital space has its own unique number of orbital spaces per shell. S orbital spaces, there's going to be one of those per electron shell or electron subshell, and that means you're going to draw one line like you're seeing right here. P orbital spaces, there's going to be 3 of them per subshell, so you're going to draw 3 lines. D, you're going to draw 5 lines, and for an F, you're going to draw 7 lines. And in green down here is a very important piece of information. To do an orbital diagram, you need to have the full electron configuration to do it properly. If you don't have the full electron configuration, you can't do the orbital diagram. All right, so I've given you a few different examples of atoms and electron configurations so that we can practice. So we're going to do carbon first, which is the one in blue up here. And I've already pre-written out the full electron configuration for carbon. This picture down here is essentially a blank orbital diagram space that we're going to fill out as much as we can depending on the element that we're doing. So you can see already that carbon has a very short electron configuration. 1s2, 2s2, 2p2. And so we are only going to fill out these 3 pieces of that diagram because carbon doesn't have that many electrons. Within that 1s space, we know that there are 2 electrons. There's only one line here because s orbital spaces, there's only one of them per shell. So we're going to put an up arrow and a down arrow to represent those 2 electrons. We're going to do the same thing for the 2s2 piece of that. One up arrow, one down arrow. Now, for the final piece, 2p2, you'll notice that there are 3 lines because in each subshell there are 3 p orbital spaces, but we only have 2 electrons. So remember, those electrons are going to be as far from each other as they can be. One of those electrons is going to occupy one line. One of those electrons is going to occupy a different line. If you had tried to draw them by pairing them up, that would have been incorrect. We can't do that because, again, electrons like to be as far away from each other as they can be until they have to start pairing up. All right? Now, that's an easy one. So I'm going to erase all of that so that we can do silver, which is going to be a little bit harder. We notice that silver has a much longer electron configuration, so we are going to fill out much more of this diagram than we would have for carbon. The nice thing about orbital diagrams is that unless you're talking about the final piece of the electron configuration, all the other lines are going to be filled with electrons because everything below that final piece of the electron configuration is full. So you can just put an up arrow and a down arrow on every single line until you get to this last piece, and then you have to start paying a little bit more attention. So what I'm going to do is I'm going to go through the full configuration and draw out the orbital diagram, and I'll cross it out as I go. First one I'm going to do is 1s2, an up and a down arrow. Then we do 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and finally our last piece of the configuration, 4d9. So we'll notice that I only put 9 electrons. I didn't fill that row. This one is left unpaired at the end. And you'll also notice that this diagram moves upward as you complete it. Everything is just a slightly different height from one another. And that height differential represents an increase in relative energy over time. So if you remember, I said as our principal quantum number, that big first number increases, we increase in energy. I also told you that certain ones tend to skip back a quantum number. So the D's and the F's. And you can physically see on this diagram that they represent a slightly lesser bit of energy than their counterparts in the P and the S. So that just kind of gives you a visual diagram to show you how the quantum number represents that distance from the nucleus and how it represents the increase in overall energy. All right, so let's erase that, and we're going to do the final one, lead, which is going to be large. But once again, all of those lines of that configuration, they're all going to be full except for that last piece of the configuration, 6p2. So once again, I'm just going to go through it until we get to that last piece. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4F14, so we actually do get to see an F row in here. D10, and finally 6P2, which is going to be our incomplete one. So once again, we need to be extra aware that those two are not going to occupy that same line, that same orbital space. They're going to spread out. So we're going to draw our last two arrows like that. All right? If you have any problems with this or understanding how I'm drawing my arrows, where I'm getting that information, please don't hesitate to ask.